heute will be given by the research leader of the laboratory, Ludmil Kацarkov. The title of his talk is Iterated Locked Iterations and New Hodge Structures. Please.
Thank you very much for giving me the opportunity to speak here. So, as always, it's very nice to be in Moscow, especially in this beautiful building of High School of Economics. So, we'll change, the talk is going to be about the same, but the structure will change a little bit. Due to the eclecticity of the audience. So, first actually I'll start with motivation. Then, so I'll introduce this old and new those structures. And then we'll basically finish with the application of this, potential applications of these new core structures to the initial motivating question. So I must say that probably the best book or best reference sources for this are some papers on applied mathematics where theory of center manifolds is quite well developed. And so I won't, of course, talk to you about anything connected with the growth of polymers or evolutionary equations, which you can find in this paper, but we'll just see how this method applies to our situation. So, okay, let's start first with the motivation for that. And that's a convenient way to more or less start where I finished last time I was talking in Moscow. So, there is the following observation that we all know that if X is a smooth projective variety, and dimension of X is equal to 1, then the universal covariant of X is C Q1 or this. This is the well-known theorem attributed to Riemann, but it was actually proven by Kelvin. And then the dimension of X is equal to 2. So we do know some examples of universal covariant. Q1 is Q1, Q2, B equals B, C equals C, and so on and so on. And so, but it's rather clear that if you want to give a completely classifying all possibilities answer, as in the case of one-dimensional smooth projective variety, that's going to be impossible, mainly due to the fact that we know very little about all simply connected surfaces of general type. And of course, with this in mind, Shepherevich did pose the following question some so we are again in the very same situation. X is a smooth projective variety, because we are asking this question in the case of arbitrary dimension. So let me just remind what the homomorphically convex means.
Yes.
Well, I forgot myself. We can figure out together. So M is a complex manifold, complex space. No? So we say that M is homomorphically convex. There's only if for every infinite sequence of points in M for every infinite sequence of points in M, there exists a homomorphic function f unbounded in infinity known on this sequence. So in addition, we will actually request that this sequence is without limit points. Homomorphically convex is without, if for every infinite sequence without limit points, we can find a homomorphic function which is unbounded on the sequence. So with this additional requirement, we can immediately see that all compact universal coverings are going to be homomorphic convex due to the impossibility of finding such a sequence. And then, more or less, this definition geometrically means that if you squeeze all complex varieties of your space, what you are going to get is a Stein space. All of these examples do satisfy this problem. So, now if you want to approach this question of Schiffer-H in dimension 2, you might want to look at the following examples. So let's say that we have a surface S, and let's say that we have a configuration of human surfaces yi. It says that each of these yi is equal to P1. And with the property that the image of H1 of image of H1 with coefficients of Z of Y into the image, into the H1 of S with coefficients in Z is infinite.
Sorry. Y is P1?
Yeah. And then, so we have a sequence of curves, each of which is equal to P1.
What do you mean then H1 of
Y, just
all Y?
Yeah.
Union.
Yeah. So, if we actually can find a situation so that this image is infinite, that would lead to a negative answer to this question of Schiffer-H. So do we see why is that? you see, if you go to the universal coloring, so you have that this configuration of curves here, open sub. Since the image in the fundamental group of the whole surface of each of the components is trivial, but the whole image is infinite, then you expect an infinite sequence of such a homomorphic curves. And then, so on this infinite sequence of homomorphic curves, in this infinite chain of homomorphic curves, we can obviously find the infinite sequence of points. And since they're compact curves by maximum connected sequence of compact curves by maximum principle, every homomorphic function in this infinite sequence of compact curves is going to be constant. So that would immediately violate this definition here of cascaded film-bounded function. Of course, this would have been rather cheap negative answer to this conjecture for average. And indeed, we do know from the work of the linear that actually this image is equal to the image of the union of H1 yi z into H1 SZ. And that, of course, as we all know, is trivial. So this is due to so-called property of strictness of mixed code structure, which was proven by Helene. So what that tells you is that basically, if the image on level of all of the associated gradients is trivial, then the whole thing is trivial. That's what trivial means. So therefore, this cheap attempt to give a negative answer does not work due to the strong restrictions coming from postulating considerations. And in fact, Post theory is a rather powerful thing, so you could consider all kinds of versions, non-abelian, non-commutative, and so on and so on. And you could easily come to the point where instead of working with H1, you will work with fundamental groups. So, as before, you have a similar situation, so you have this surface, and you have a sequence of curves with the properties of the image of pi 1 of yi into the image of pi 1 of s is equal to 0, but the image of pi 1 of the whole configuration in pi 1 of the whole surface, of the surface itself is infinite. So if you can arrange such a situation, then this would mean that you have this infinite chain, and something that happens, then of course that would give you a negative answer to this conjecture of superimage. So now the fundamental group itself doesn't have a box structure or mixed source structure on it, but you can modify this a little bit and consider something which is called relative completion with respect to some representation. And that is defined in the following way. So you consider a representation of your fundamental group into the GLMC. And you leave this to an extension of your image here by nilpotent groups. And so this infinite system, projective system of groups, actually defines an algebra. And so this algebra is called relative completion of the fundamental group of your curve for surface. And let me just say that in the case when this is trivial representation, you just get the standard algebra associated with the massive completion. And these are known to have a mixed cost structure on them. So by the same token as before, you can prove that if this is equal to 0, then this is equal to 0. So you get the following statement. So I'll make I will delete this statement, although stronger statement is correct. So let's say that phi 1 of x is containing LNC. Then this implies that the universal element of x is homomorphically convex. So of course, I consider only surfaces here, but it is known that absence of this infinite change is pretty much the only abstraction to homomorphic convexity, as follows from the work of Napier and Narasimhan. And then, of course, Koch's theory is usually very functorial. It behaves well under hyperplane sections, so you can actually reduce from higher dimensions to the surface case and make an argument similar to what I was explaining here. Of course, I mean, this is hard work and requires quite a bit of analysis and clearing this out. Well, of course, there is no need for our fundamental group to have any representations. And in fact, this requires a little bit more, that this is actually a subgroup of GLNC. And there are fundamental groups which behave in wild way. So this way of arguing does not work for them. So the question is, are there such fundamental groups which do not are not covered by this method, and what would
sorry, the arrow goes the other way, right? From pi 1s to gamma I or li or the vertical arrow.
Ah, so. I hope, yes. Okay. So, what do we do in the case if these groups do exist? Well, in fact, the existence of such a groups, and more or less this group theoretic content of this question of super H, was something was definitely subject of quite a lot of work a long time ago, and certainly should be connected with the names of Ludmil and Perrier. So I'll briefly mention this connection, although I will not have that much time to elaborate on it. But this is the type of groups where we're actually aiming our theory at. So I assume, since we are in Moscow, Bernstein theory is very well known. Yes, no? Theory of Bernstein groups. I thought Moscow is the Mecca of Bernstein theory. All right, so let's, I mean, it's a British subject, but was mainly developed by Russians. So, let's make a small excursion. So the Bernstein group so it's defined as follows. So we take a free group of n generators and we mod out by the relation xd equal to 1 for every x in Fn. Okay? So let's do some examples. So V and 2, that is equal to V 2 to the power n. That's we can easily check. So B and 3, it's also finite. That is a nice exam problem. So B and 4 is also finite. Of course, that it's not such an easy theorem that belongs to Samov. It was proven during the Second World War. So, here 5, I don't think this is known, but I please check this with Zelmo very recently. That's known to be finite. It's a hard theorem by Philip Koch. And so on and so on. So it a natural question asked by Bernstein is that can we find n greater or equal to 2 and d big enough so that d and d is infinite.
What do you mean by can we find n and for every n?
Well, so it's in. And so the theorem proven by Novikov and Adyan I apologize, I have to follow the old Russian tradition of putting first the name of the person who was more important in the society, not going in the alphabetical order. But so this is Piotr's abbreviation. And so the theorem states that B and B is infinite for n greater than equal to 2, and the odd and greater than 1 for 57. I make a mistake, I could be wrong. So later on these records were broke down. But there were other developments. So using geometric group theory, Gromov came with a completely different proof of this statement on half a page, and then in a book of about 400 pages, Ushansky described his idea of Gromov in full details. So, in fact, he proved much more, that anytime we have a hyperbolic groups, of which Fn is one of, so after a certain big number, which depends on this curvature in the sense of Gromov, you actually get an infinite quotient. So in particular, so you can do similar thing for the fundamental group of a Riemann surface. And again, after some big enough number, depending on the unit, this is going to be infinite. So now, of course, Burnside theory has many other questions, and so one other of the Burnside questions was I won't actually state this question. It will lead to bastardizing the whole work of Zelenon. Let me state the following theorem. So B and D is non-residually finite when infinite. That's part of the work for which Zelenon got his medal. And Zelenon on his own also did pose the following question. That question is very natural, as we can see, but actually was posed by Zelenon after he learned this work of Ludmil. And the question is, can we find n1 that should equal n2, and dt such that B and V n to V is infinite. In other words, is there such a threshold?
Should it be vice versa?
Sorry?
Should it be vice versa?
No, the smallest one is finite and with a bigger number of generators in this universe.
Oh, okay, so it's
you
the same
keep
D.
you keep the exponent the same, you
Yeah.
increase the number of generators with their threshold. So this cardinality jumps.
Can you please also remind what's non-residually finite?
So,
Okay, thank
but let's kind of fix it. So group G is non-residually finite with the intersection of the normal finite index. So it's residually finite. So the subgroups of G and C are residually finite. So now, very briefly, how these questions in Bernstein theory are related to our initial question. Some other traditions in Moscow still actually go on. I do remember the first time I met Maxim was in some pro seminar that was led by Kirov. And at that time it was really hard to find any kind of eraser of the board. So since Maxim knew what we were talking about already, he was sent to find an eraser, and it took him about 20 minutes to find one. So he was able to already solve pretty non-trivial tasks already at that time. The religion seems to be not common. So in any case, so what Umov actually proposed was that there is a connection between this discussion that we have here on Bernstein groups and this Umov convexity question because of the following thing. So we have a surface which is a vibration of Riemann surfaces over a curve C, and then we take a coloring, which is D1 coloring, and so you take this coloring to be a coloring ramified precisely. So you take D1 coloring for the base curve, which is ramified precisely at the points here where, over which we have singular fibers. So now, by doing that, you notice that if something was a vanishing cycle here, so upstairs, it is actually, this is the vanishing cycle gamma. Downstairs, upstairs, what actually vanishes is gamma in power t. And so, I mean, if you look at these components here, these singular fiber with many components, their Riemann surfaces are smaller genus, and so the image of their fundamental group in the fundamental group of the whole thing is on the level of gamma, sorry, phi 1 of G, 1 modulo gamma, and then upstairs becomes Burnside type of group. And of course, the image of the fundamental group of the whole fiber is P1, so it's phi 1 of G2, again, modulo gamma in power P. So now the importance in the hard part of the construction is that you actually using the monogamy can get all the elements. But that indeed is something that was done by Delinear. And indeed, this image of the whole fiber upstairs looks like the Burnside group that types the Riemann surface of genus 2, G2 bigger than the Riemann surface of genus G1, which is the image of the fundamental group of these components. So if you can arrange this happening, so you will get a negative answer of the this question of Shepard-Edge, which is pretty much related to this positive answer, to this question of Zelman. Of course, I was told by Zelmanov that this is a very hard question, and group theorists do not even have an idea how to approach this. So he was thinking that maybe one can actually prove the Shepard-Edge conjecture, and after that, due to this relation, which I described very vaguely, they will have the answer of the this question as well. So I say that the opinion of group 2 is different on that. Zelman thinks that there is no such a threshold, and Olshansky actually thinks that it's good. All right, so what to do in the case when our groups are of this very complicated, non-residually finite type? So the proposal is to, again, imitate Koch's theory, but a little bit different, more oriented to applied mathematics way. So I'll have to skip a little bit from what I had planned and go immediately to the following example. Let's say that we have a extension of variations of Koch structures, variations of mixed Koch structures. And so this can be taught as Higgs bundles. So we have one big Higgs bundle. So on each of these variations of mixed Koch structure, we have a harmonic metric. And on the space of all these harmonic metrics, we have an equation which is given, so this is for on this big space of metrics, infinite space of metrics. So this equation is given like H inverse dHdt so F is infinite dimensional space of metric. So this is a modification of so-called Donaldson equation. But methods from applied mathematics applied to this situation actually tell you that you can reduce this very complicated equation to a finite, an equation, OD, on a finite dimensional space. So let me briefly illustrate to you how to do that in this very simple case. So to this situation, you correspond to a quiver. So to each of the these pieces of this mixed structure associate a vertex, and then these arrows, they give you the extensions between these mixed structures. So now, instead of having this complicated equation, you can actually get an equation on finite dimensional space in the following manner. So again, to this quiver, instead of working with the representations of this, we work with metrized representations. In other words, to each vector space associated to the vertices, we associate a metric. And we consider the following differential equation on this matrix here. So it is basically modification of King's equation. King, who kind of came very close to this. This was a problem given to him by Donaldson, but Donaldson told me then he moved to do things, stupid things like zero symmetry, so he stopped working in this direction. But in any case, mirror symmetry is very much into this consideration, so probably we won't have time to discuss this today. So what Kings did is wrote the following equation. So it's the inverse then, so let's denote this the alpha from I to j, where I and j are the vertices. Sum of dg inverse the alpha alpha. This is the King equation. And so this is an ODE which has a finite dimensional space of solutions, and these equations, these solutions actually give you the certain asymptotic behaviors of your metric. So the solutions of this equation, so one can compute are the following form. So it's V0, sorry, it's V1t plus V2 log of t plus V3 log of t plus and so on plus so on. has the following asymptotic behavior. So when we move with this flow, so we can actually reduce our infinite space of metrics to a finite dimensional space. And so this finite dimensional actually space is called central manifold. That's why I'm the last. Well, you see this is known here before, but central manifold. So now the theory of variation of mixed form structures actually can be completely repeated, but this time, instead of working with the spaces themselves, we work with the extensions. So this manifold basically parameterizes the extensions that we have in this quiver, and then the solutions have this asymptotic. Of course, this situation is very developed in ordinary differential equations. So the methods of bifurcation diagrams and their variations this time actually measure the extensions of mixed form structures. So in fact, you can answer already here rather interesting, at least unknown, according to Simpson and Griffith's answer to the following question: when an extension of a mixed form structure is a mixed form structure on its own. So this approach allows you to answer this. But I won't have time to tell you how this Griffith's transversality, which we can associate with this variation of central manifolds, answer this question. So I would like to keep close to the initial question we have started with, namely about this homomorphic convexity. So the mirror of this picture, where we consider vector bundles or flat mixed form structures or some variety, is the following. So we have the role of the vector bundles is played by Lagrangians, let's say Lagrangian spheres. And the role of the extensions is played by the polar homology between this Lagrangian. And you can write similar equation to this one, which in this case is going to be the, this one, which is going to be the mean curvature equation. And so this very complicated partial differential equation, in this case, is reduced by ordinary differential equation associated with the quiver. So the behavior of this very complicated Lagrangian in limit is described by relatively simple data associated with the differential equation with this quiver. So in fact, this is a complicated example, but the example we need for our purposes is just in dimension 1. So now I'm going to have a Riemann surface with some functions, and then we have Lagrangians, which can be treated as elements of the fundamental group of this Riemann surface. quickly they approach these punctures on this Riemann surface. So as before, this very complicated Lagrangians on the Riemann surface can be completely recorded by the behavior of finitely many of them around this point. And so again, as before, we have some quiver which tells you that. So now, these extensions, as before, gives you a central manifold. Once again, so this is something to which our system kind of converges, so it goes very fast initially, and then the whole data is recorded by this five-dimensional manifold. In this particular case, this very complicated Lagrangian, or elements of the fundamental group, they are recorded by the behavior of the asymptotic limits around these functions. So now in this situation, the extensions here, again, form a finite-dimensional manifold, as I said, the central manifold. And so these central manifolds do behave in a functorial way, and well, this is rather surprising, but true is that if you get some morphisms between Riemann surfaces, the central manifolds associated with the corresponding mean curvature flow satisfy this strictness property with which we have started. So the whole story is that if you start with these complicated equations, you can actually reduce this to some kind of central, to this kind of central manifold, and some properties very similar to classical Hort structure do hold in this situation. In fact, before we had this strictness property for mixed Hort structure, now we have this strictness property for central manifolds, which are not Hort structures, but they, in some cases, measure extensions of mixed Hort structures. But still, they do satisfy this kind of nice properties, punctuality, and strictness. And so the hope is that this new discovery, which definitely can be described in categorical terms, would allow us to crack this initial question by Shafarevich and get hopefully a positive answer, which of course will be a negative answer to this question that was posed by Zelman. So I'll stop here.
Please put your questions.
Can you say something more about the strictness property? Because before you had mixed Hodge structures, and now you have some manifold with an ODE. And
well, so this strictness property, once again, is responsible for the extensions of your object. So this could be completely described on the language of modular lattices, namely, let's say that we have a modular lattice and modular sublattice. And then to a modular lattice you can correspond to an ordinary differential equation and a central manifold associated with it. And then if you have a sublattice, the truth is that the central manifold is the restricted central manifold. And now if we have morphism between lattices, so the fact that the image of the central manifold is trivial applies to your initial lattice. Actually, it was not in a trivial way. So that's the right way to talk about this. Modular lattices for some people are simple, for some are not so simple, so I prefer not to discuss this here. Of course, I mean, this is just one application here. I mean, things I do expect to apply to some parts of our theory. It's a much more general situation in which this applies. Yes?
Can you say a little more about your original, the first example that you talked about, the relative completion?
Yes?
I don't quite see the logic because, I mean, the leads, of course, involves the fact that it's a pure Hodge structure. And so
No, it's a mixed Hodge structure.
yeah, that's my question. I mean, in your first example that didn't work, you argued that because it was a pure Hodge structure, of course, you couldn't have an infinite image.
meaning with the H1.
So when you have your configuration of rational
But I
curves,
was looking at H1.
yes, H1 of,
Yeah, so H1 of the singular curve, which Y is singular,
yeah,
is a mixed cost structure.
yeah, I understand.
So all I was saying is that the associated grade are these pieces that come from
Absolutely,
Y.
absolutely, so I understand. But now you say you want to go to where your target is a mixed Hopf structure.
Yes.
And there it would seem that there is no obvious constraint to having your mixed Hopf structure on your configuration of curves go non-trivial.
Yeah, what I'm saying, claiming that there is.
Oh, there is?
Yes, so,
Okay, that's my
but
question.
it's not recorded by, it's recorded by this central manifold, which measures how the extensions come together. On the language of ODE, so we have this variation, which gives you a variation of central manifolds. And this central manifold may have bifurcation diagrams on it, which we all learned a long time ago from Arnold. And so if you actually come from extensions of mixed cost structures, there is a restrictions on the way these bifurcation diagrams behave, and that puts a lot strong restrictions on the situation.
So there's some sort of finer structure.
That's correct.
More questions? If not, let me send this to you. Coffee break is on the ground floor. Значит, кофе внизу, в буфете. И ко всем еще просьба, как всегда, есть листочек регистрации. Распишитесь, пожалуйста, кто пришел. Да. А кофе внизу в буфете.
My name is Olga. I'm an editor. Oh, nice to meet you. Yeah, I didn't know it. But now it's a coffee break with a very good Russian. Yeah. Вот, интересно? Да, да. Особенно в телефоне.
Пойдем.
Давай, подпись поставь, пожалуйста. Конференции записывайте, ребят. Нет, не кончится. Иди сюда. Вот так. Главное подпись у него. Так, давай.
Она собака не
Работа, да. Сереж, значит, есть место, я написала, значит, честный номер. Да, пришли мне как замок, место работы и звук. Нет, я зарезервирую сейчас, зарезервирую имя, я расскажу. Нет, ну напиши мне на мой, да,
Даже приходит стоит
как работает его жену, его и место их работы, она тоже работает.
Где работает? Я могу
Не надо, я нужно ее место работы и... Да, все, мне не отчество.
Вы его очень
У нас докладчик не написано.
Ну, очень прям не является.
Ушел. Кофе брейк.